Okay, today I want to talk about, get into organic chemistry a little bit more, and I want to start discussing functional groups. So I want to do a little bit of review of shorthand organic chemistry, how to draw the structural formulas for these compounds using shorthand, just so you're familiar with what that looks like. So, like if you opened up a organic textbook or you looked up some organic stuff online, a lot of times you might see the shorthand drawing of an organic structure, and I just want you to be able to interpret that. And then after that, also, so talk about the structure of those compounds a little bit, but also then talk about functional groups. So now we're moving up the game. So the organic we've talked about so far has just been hydrocarbons, so things containing only carbon and hydrogen. And now we're going to add some different things to those molecules. So what happens if I take a hydrogen off and I put this on? What happens to the molecule? Um, so and those are functional groups. So that's what we're going to get into today. And and then I'll kind of highlight the things you need to know about the functional groups. So it's not necessarily knowing that the functional group is called this, but it's understanding that if you have that functional group, it changes the polarity of the molecule, which then changes the types of intermolecular forces it has. It might change if it's soluble in water or not, and it'll change its boiling point and all that stuff. So that's what we want to talk about. All right, so let's jump into it. All right, so again, let's just kind of review a little shorthand. So if I said to draw hexane, so let's understand a hex in or our organic naming system means 6 carbons, and then ane means all single bonds. And remember, the other word for that is it's saturated. So all the carbon-carbon bonds are single. So if I wanted to draw it, right, this is how we're to draw it. I have to draw 6 carbons in a row, all single bonds, right? And then I'd have to fill in the octet for each of the carbons by adding hydrogen, single bonds. So the carbons on the end are going to need 3 hydrogens to get 8 total electrons around it. And then the carbons in the middle are going to each need 2 hydrogens, right? And, you know, you can understand that if you had to draw hexane over and over and over again, it could get a little annoying, right? Drawing this big molecule. And, you know, a lot of organic molecules are even bigger than this and have more carbons and more hydrogens and other things. And it gets a little tedious drawing these dot structures over and over again. So that's one reason why the shorthand's a nice way to simplify that a little bit. But also it gives us a better, I think, idea of the shape. You know, because we've been calling these straight chained alkanes, right? Straight chains means all the carbons are lined up in a row. But really, if you looked at the shape, if you were talking about the 3-dimensional or the Vesper theory shape around each of these individual carbons, each of these carbons have 4 bonding domains around them. So each carbon is going to be tetrahedral in shape. So tetrahedral, tetrahedral, tetrahedral. So, you know, the way this molecule looks right now, drawn on my piece of paper, is really not a good representation of what it looks like in 3 dimensions. And I think the shorthand gets a little bit better idea, okay? And so the shorthand is just kind of this zigzag thing, all right? And this is equal to this, right? This just 1, 2, 3, 4, 5 lines, but 6 points. 1, 2, 3, 4, 5, 6. That's our shorthand notation for hexane. So here's the full structure of hexane, here's the shorthand. And so the way the shorthand works is every time the line segment kind of changes, that's a carbon atom. So I got a carbon atom here, 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 here. So I got 6 carbons. And then the hydrogen is understood, right? So if I just have a single line, that means a single bond between this carbon and this carbon. Okay, so this carbon's going to need 3 hydrogens because it's at the end, right? So right there, that's that carbon right there in the regular structure, 3 hydrogens. And then each of the middle carbons would end up having 2 hydrogens. And so each end carbon has 3 and each middle carbon has 2 to satisfy the octet. So that's all we would have to draw if I wanted to draw hexane, okay? And then you're not going to be responsible for naming naming or writing the formulas for things other than straight chained alkanes, alkenes, and alkynes. But there are such things as cycloalkanes, alkenes, alkynes. And cyclo or cyclic hydrocarbons just means they're in a ring structure. Cyclo means in a ring, circle kind of, versus a straight chain. So I'll show you the example. So this is our normal hexane. Okay, but then you could have cyclohexane. So that means this, you have 6 carbons, but they kind of come back on each other. So they're in a ring structure. So 1, 2, 3, 4, 5, 6 carbons in a ring. So that's cyclo. Cyclo means they're in a ring versus, just hexane, where they would be 6 carbons in a row. Now they're kind of coming back around. And each of the carbons would end up with 2 hydrogens on them to satisfy the octet. So we would end up, cyclohexane ends up with 2 less hydrogens than regular hexane because all the carbons are bonded to each other instead of the N carbons on normal hexane needing 3 hydrogens. In cyclohexane, you're only going to need 2 hydrogens on each carbon, okay? But again, I'm just showing you this to show the shorthand. So if you see a hexagon, right, in your chemistry textbook or in online, that's representing cyclohexane, right? Carbon, 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 and then it's understood 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens to satisfy the octet. So that's our shorthand structure for cyclohexane. Hexane, shorthand, cyclohexane, okay? So just kind of an idea. Now, we could add double bonds to our shorthand, and this is all we would have to do. So here's 2-hexene, the double bond between carbon 2 and carbon 3. So we have 6 carbons in a row. We have a double bond between those 2 carbons. So this is how we would do the shorthand. So we would do our 6 carbons in a row, and then a double bond. Now, that double bond there means now this carbon only needs 1 hydrogen, and this carbon only needs 1 hydrogen, and that's understood. It's understood that the carbon can only support 4 total bonds. So if you got 2 bonds here, this carbon has 1, 2, 3 bonds, so it only needs 1 hydrogen, right? This carbon right now only has 1 bond, so it's going to need 3 hydrogens over here. And kind of look how it's parallel, right? This carbon matches that carbon, so this carbon has 3 hydrogens, just like that structure. But this carbon matches that carbon, and notice it only has 1 hydrogen. Okay? So what if there was a triple bond? Well, you guessed it, 3 hexine, you have 6 carbons in a row, you would go to carbon number 3, and you would show your triple bond. Okay, so we can do shorthands for alkanes, we can do shorthand for alkenes, we can do shorthands for alkynes, okay? So just kind of an idea of what that looks like. All right, now let's talk about the functional groups, all right? So now we're changing the game, all right? So hydrocarbons only had carbon and hydrogen. And again, in terms of naming and formula writing, you're really only gonna have to do hydrocarbons, all right? But you need to be able to recognize different functional groups and what that means to the structure of your molecule. All right, meaning what does it do to the polarity of it, and what does it do to the types of intermolecular forces it has, all right? So functional groups are things other than hydrogen and carbon we throw into the organic compound, okay? And they're called functional groups because they change the functionality, they change the classification of the compound, all right? So let's understand something. Hydrocarbons, by definition of being polar, are nonpolar, all right? So hydrocarbons don't have any polar bonds, right? The only types of bonds hydrocarbons have are carbon bonded to carbon. Now, this could be a double bond or a triple bond, but it's nonpolar. Carbon bonded to carbon is 100% covalent nonpolar because there's 0 electronegativity difference. And remember, this electronegativity difference in a CH bond is negligible, and so we want to know that that bond is nonpolar. So you can't be a polar molecule if you don't have any polar bonds. So hydrocarbons, since they only have carbon and hydrogen, by definition, are nonpolar. Which means, so what should we take from that? Hydrocarbons are not water soluble. Remember, our rule for solubility is like dissolves like. Water is polar. Hydrocarbons are nonpolar, so they don't dissolve in water, right? And also, they have weaker IMFs. Hydrocarbons have weaker IMFs because they're nonpolar. They only have London dispersion forces. Now, those London dispersion forces can be really strong for really big molecules, because the bigger the molecule, the bigger the electron cloud, the more electrons the molecule has, the greater the London dispersion. So it doesn't mean that all hydrocarbons have weak IMFs. It really just means the only IMF that a hydrocarbon has is London dispersion. And if it's a smaller molecule, it's going to be very weak London dispersion. But if it's a really big molecule, it could be very strong London dispersion. But the only intermolecular force it has is London dispersion. So remember, hydrocarbons are oils, basically, right? Octane, gasoline, right? So we know oil doesn't dissolve in water, and now we know why. Oil is just a hydrocarbon. It's nonpolar, so it's not very water soluble. Remember, our rule is like dissolves like, right? But now we're going to enter in the functional groups. So the functional groups change this. A functional group, understand, if we throw in a functional group, now the molecule is going to be asymmetrical. Now the molecule is going to have some polar bonds. So now the molecule is going to be polar. So hydrocarbons, organic compounds with just carbon and hydrogen, nonpolar. Now, if we have organic compounds that contain more than just carbon and hydrogen, they have these what we call functional groups. Now they're instantly polar. Instantly polar. And what does that mean? It means now their strongest IMF isn't London dispersion. Now their strongest IMF might be dipole-dipole interactions or hydrogen bonding, right? Because they're polar. If there's a functional group, it's polar. And now the question is, does that functional group contain a Fon bond, so it can have hydrogen bonding capabilities, or does that functional group not contain a Fon bond, so it just has dipole-dipole interactions, right? But what we want to know is, all of a sudden, we throw in something other than carbon or hydrogen into our organic structure, the molecule's polar. Boom, all right? Now, there's tons of functional groups, okay? There's tons of functional groups, and we're not going to spend a lot of time on them. We are going to show you kind of the more common ones and the ones that you need to recognize. But if you just do a simple Google search, I'll show you. Google search organic functional groups, and you'll get a ton of charts, right? Like here's a bunch of functional groups, right? Here, alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, amines, amides. There's so many different functional groups. So you're not going to be responsible for all of these. You're just going to for a select few. If you go to your guided notes, there's a chart in here. Here are some common functional groups, okay? And notice they all have the kind of same name here, okay? And I want you to understand how to read this chart. R just means the carbon chain extends this way. So you have a carbon chain, and it could be 100 carbons over here, or it could just be one carbon. But what we're saying is an alcohol is an OH group attached to one of the carbons in your carbon chain, right? The way to read this, what an ether is when you have an oxygen kind of interrupting the carbon chain. So you have a carbon chain this way and a carbon chain this way. And so it might be 100 carbons, carbon, 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 and then all of a sudden an oxygen, and then carbon, 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 carbon. So it could be 2 carbons this way, 3 carbons that way, that doesn't matter, okay? But if your carbon chain is interrupted by an oxygen, that's what an ether is, right? So, and again, I'm gonna show you on my notes here in a second, the difference, but an aldehyde and a ketone, it's the same functional group, it's a double bond O, but it depends on where that double bond O is in the chain. Notice an aldehyde, the double bond O, is on an end carbon. Notice that going this way, it only has hydrogen, so the carbon chain stops. But going this way, the carbon chain could continue forever that way, right? Whoops. So that would be an aldehyde when the double bond O is on one of the end carbons. But notice when the double bond O is on a middle carbon, so notice you could have, if the double bond O is on this carbon here, and it's in between carbons, so carbon chain extending that way and carbon chain extending that way, now all of a sudden that functional group makes the compound a ketone, whereas that same functional group, but at a different location, makes the compound an aldehyde, all right? So let me get into the functional groups that are kind of important to us, all right? So the first functional group, technically it's called a hydroxyl group, but you can call it an alcohol, Because really what it is if you have an OH, okay, if you have an OH attached to your hydrocarbon, that OH is called a hydroxyl group. And if that's the only functional group you have, the compound is classified as an alcohol. All right, so the functional group's called hydroxyl and the classification is called alcohol, but you could just call it an alcohol group. Okay, a lot of times hydroxyl and alcohol is interchangeable. And I think the more important name to remember is alcohol, because you got to know that, oh, I have an OH. This is an alcohol. This is not an alcohol. So let's understand. So here's methane, right? We know methane already. We know it's a hydrocarbon and we know it's nonpolar. All of a sudden, if I take one of those hydrogens and I replace it with a hydroxyl group, an alcohol group, right? Now this compound is an alcohol. And the way we would name an alcohol is with the OL suffix. So instead of methane, we say methanol. OL means you have an OH group. OL means you have an alcohol group, okay? So it's an alcohol, but notice what that does. Now this is a very polar bond. This is a very polar bond. The molecule now has polar bonds. The molecule now is asymmetrical, so the molecule is polar. Not only is it polar, look, we have one of our Fon bonds, H bonded to O. And if that's the case, then methanol can hydrogen bond with other methanol molecules. So this guy's strongest IMF, methane, is just London dispersion, and it's pretty weak London dispersion because there's not that many electrons. But you go over here, methanol, this has hydrogen bonding. Methanol is a liquid at room temperature. Methane is a gas. The reason why methanol is a liquid is because it has strong intermolecular forces, right? Methane has very weak. So it takes a lot more energy to break these IMFs than it does over here. And that's what boiling really is. You have to break the IMFs. And so the stronger the IMFs, the higher the temperature the substance boils, right? Okay. So understand that, we could draw methanol this way, but understand, like, around the carbon, like if we're thinking in 3 dimensions, this is a poor representation of what methanol would look like, right? Around the carbon, you have tetrahedral geometry, but around the oxygen, it's not linear, it's bent, right? 2 lone pairs, 2 bonds, it's bent. So I guess this would be a better representation. Tetrahedral around the carbon, bent around the oxygen, right? So bent around there, tetrahedral around there, okay? And again, now we can show you the hydrogen bonding it has. So why is methanol, and not just methanol, why do alcohols mix well with water? Why are they soluble in water? Because they are polar, just like water, because they can hydrogen bond just like water. And you can show a hydrogen bond between a methanol molecule and a water molecule. So here's a methanol molecule, here's a negative dipole on the methanol, here's a positive dipole on the water. So that dipole-dipole interaction right there is really a hydrogen bond, okay? All right. And then also notice the OL ending. OL means alcohol group. All right. So if I had hexane, that's just 6 carbons in a row. But if it was hexanol, I know somewhere one of the hydrogens is replaced with an OH. So it could be over here, it could be over here, it could be over here. But here would be a shorthand version of hexanol. And I have to replace one of the hydrogens with OH. Okay. I see that OH on an organic compound, I should think alcohol. Okay, if I see the OL ending in the name, I should think alcohol. Okay, and what do I need to know about alcohols? Alcohols are polar and they can have hydrogen bonding, so they're very water soluble, strong IMFs. Okay, all right, so let's talk about the next functional group, a carbonyl group. And a carbonyl is just a double bond O. But really what we want to understand is the difference in classification. You can have double bond O and it's a ketone, or you could have double bond O and it's an aldehyde. Okay, so when the double bond O is on one of your middle carbons in the chain, we call it a ketone. If the double bond O is on one of the end carbons in the chain, we call it an aldehyde. Okay, and again, so R versus R prime here, it just means here's our carbon chain continues that way and it continues this way. So this is one of our middle carbons, so ketone. Here, R only extends this way, so the carbon chain only extends this way, doesn't extend this way, so that means this carbon right here is represented as an end carbon, so that's why it's an aldehyde. So it's the same functional group, double bond O, it just depends on where the double bond O, whether it's an aldehyde or a ketone, all right? So this would be a ketone. Why? Because a double bond O is on one of our middle carbons. Here's the shorthand, right? I have 4 carbons, double bond O on that second carbon, okay? And we would name it butanone. So if it was just 4 carbons and hydrogens, it would be butane, right? But now we add a functional group, so we change the suffix, and this is a ketone, so we say butanone. So when you see an ONE ending, okay, I know it's one, but we say own. When you see that own ending, you know you have a ketone, okay? So same kind of structure. I have 4 carbons, so I'm still looking at but but now the double bond O isn't on one of the middle carbons, it's on one of the end carbons. Here's the shorthand version, okay? So now that double bond O, where it is on this compound, makes it an aldehyde, and the way we name it is butanal. Aldehyde. Ol, alcohol. Own, ketone, okay? Own. My Philly accent is coming out when I say own. All right, so let's keep going. Now we're going to combine 2 functional groups. A carboxyl group. A carboxyl group is a combination of hydroxyl, alcohol, right, and carbonyl. So it's an alcohol group, which is an OH group, and a double bond O, okay? Now, it's called a carboxyl group, but it changes the compound to an acid. Sometimes we might call it an organic acid, but better yet, it's known as a carboxylic acid. So when you have this group, it's a carboxylic acid group. And so it can only be on one of the end carbons. So you can only have this functional group on the end of a carbon chain. So here's carbon. It's got a double bond O, but it also has an OH. So it has the hydroxyl group. It also has the carbonyl. But when the same carbon has both, the same carbon has both those groups on it, that's a carboxyl group. And it makes the compound a carboxylic acid, okay? All right, so here's ethane, right? Just hydrocarbon. We know ethane is nonpolar, London dispersion forces only, and it's not very soluble, right? Not water soluble because it's nonpolar. But if we go to ethanoic acid, right? So there's our carboxyl group, our organic acid group. The way we change the ending is oic acid. So the way we would name this is ethanoic acid, okay? And ethanoic acid is really the same thing as acetic acid. Ethanoic acid is the organic name. Acetic acid is just kind of the regular acid name. It's the same exact thing, all right? But notice it's got a functional group now, so it's polar, it's asymmetrical with polar bonds, and it's got a Fon bond right there. So ethanoic acid, just like alcohols can hydrogen bond, carboxylic acids can hydrogen bond. So very water soluble, okay? And just another thing real quick, if we go back to aldehydes and ketones, I didn't mention this, but these are gonna make, these functional groups, aldehyde, ketone, make the molecule polar, but notice we don't have a Fon bond. So aldehydes and ketones are polar, but their strongest IMF is dipole-dipole interactions, whereas alcohols and carboxylic acids, since they do have one of our Fon bonds, they're polar, and because they have that bond, their strongest IMF is hydrogen bonding, okay? And also I wanted to talk about shape a little bit, right? So around this carbon, we got tetrahedral geometry. Around this carbon, 3 bonds, 0 lone pairs, we have trigonal planar geometry. And around that oxygen, it would be bent, right? So a lot of times you see it like this, but you know, imagine you have another bond coming off of this carbon. This would be trigonal planar. And around this oxygen, it wouldn't be linear, it would be bent. 2 lone pairs, 2 bonds isn't linear. Even though a lot of times we draw it that way, that's not what it is. Remember, it's bent, okay? Okay. So the last one I want to talk about is amine. If you see an amine or an amide, it means you got nitrogen in there. An amine group is an NH2 group, and you got a nitrogen in there. And notice the nitrogen has a lone pair on it. A lot of times that's not drawn. So around the nitrogen, this shape would be trigonal pyramidal, right? 3 bonds, 1 lone pair. So it's really not a good representation of the shape, but that's called an amine group. And we would call this methylamine, 1 carbon, right? So Methane, it would just be a hydrogen here, but we replace that hydrogen with this amine group. Now it's methylamine. It makes the molecule polar. We got polar bonds, and you got one of your fond bonds, H bonded to N. So amines will be able to hydrogen bond just like alcohols and just like carboxylic acids. Okay. Now, you know, organic chemistry can get really complicated. Again, I took 3 semesters of organic chemistry in college. There's Orgo 1, Orgo 2, advanced organic. So we could spend years talking organic chemistry, but we're only going to spend one little segment of a unit on it. So understand it can get complicated. But just kind of some things to throw in. Now that you know some lingo, right? I have an acid group, carboxylic acid group. I have an amine group. I have an acid group and an amine group on the same thing. You guessed it. This is called an amino acid. You got an amine group, you got an acid group, amino acid, right? This isn't what amino acid is. You can have many different types of amino acids, but to be an amino acid, you got to have an amine group and you got to have an acid group, right? That makes sense, right? You're not going to have to name this or anything like that, but just kind of, start, okay, amine, acid. I remember something in biology I heard, oh yeah, amino acid. Okay, great. Now we kind of put kind of a face to the name, right? And then just some quick suffix things to remember. If you see OL, that means alcohol. If you see ONE, one, that means ketone. If you see al, that means aldehyde. If you see oic acid, that's an acid. And if you see amine. And there's other ones, ethers, esters, all that stuff. And if you want to check that out, you can check out your chart, but these are the ones that come up the most, okay? So what do you need to know about the functional groups? You need to know that if you have a functional group, now the molecule's polar, which means now it can have dipole-dipole interactions or hydrogen bonding. You want to know alcohols, acids, and amines have hydrogen bonding because they have fond bonds. But aldehydes and ketones don't have a fond bond. So aldehydes and ketones, they're polar, but their strongest IMF are dipole-dipole interactions, whereas alcohols, acids, and amines, their strongest IMF is hydrogen bonding, okay? So now we can start answering questions like this. Why is propanol a liquid at room temperature, whereas propane is not? Well, propanol is polar with hydrogen bonding, whereas propane is nonpolar with just London dispersion forces, okay? And remember, stronger IMFs means higher boiling point, okay? Stronger IMFs means maybe at the same temperature, something's a gas and something else is a liquid, or something's a liquid and something else is a solid, all right? That's what IMFs tell us, okay? Why does propanone have a lower boiling point than propanol, okay? Well, propanone is polar with dipole-dipole interactions, but propanol is polar with hydrogen bonding. So hydrogen bonding a little bit stronger than dipole-dipole, so we'd expect the propanol to have a higher boiling point than propanone. Even though they have similar London dispersion, similar number of electrons and that kind of thing, similar size molecule, because we have that fond bond, hydrogen bonding, and then no lack of fond bond over here, only dipole-dipole interactions, right? Okay, so that wasn't as brief as I wanted it to be, but hopefully that helps out with functional groups and shorthand. Have a great day.